This is the second lecture from Chapter 20, and this lecture will focus on the kinetics of radioactive decay. Radioactive decay is always a first-order kinetic process, and that means when you plot the natural log of the quantity of substance you have versus time, you should get a linear relationship. I mentioned in the first lecture that if we look at the nucleus, we would see a bunch of protons and neutrons packed very tightly together in the nucleus. And of course, protons have a positive charge. So basically, a nucleus has a whole lot of positive charges repelling each other, all crammed together in this dense, tight little space. That's a lot of repulsive force. So what's holding the nucleus together? What holds the nucleus together is what's called the strong force. Very creative, huh? It is literally the strongest force known to mankind. Okay, strongest. It should be called strongest force. Strongest force known. And that is kind of some invisible force that holds the nucleus particles together. And when we have nuclear decay, so when a nucleus is unstable, really mostly because of this repelling force between the protons, so when a nucleus decays, what happens is that strong force, the energy that holds it together, is released, some of the strong force. So that releases some of the strong force. And that is the tremendous energy we get from nuclear reactions, whether it be a nuclear bomb or nuclear energy for our homes. It is release of the strong force. And as you would expect, the neutrons, which have no charge, play an important role in stabilizing the nucleus. You can think of them as kind of a dilution for the repelling force between the protons. As a result of that, the neutron to proton ratio in a particular atom is very important and in part determines the stability of that particular atom. Okay, if you have too many protons, the repelling force between them is going to become too strong and the nucleus won't be stable. We have something we call the valley or band of stability, and this might show up not only on your final but also perhaps as a multiple choice question on your exam, where on the y-axis is the number of neutrons in a nucleus, and on the x-axis is the number of protons, which of course hopefully by now you've noticed chemists call Z. And the first 20 elements or so, the ratio of neutrons to protons is 1. Okay, 1 to 1. And that makes for stable atoms. None of these atoms that have an atomic number from 1 to 20 are radioactive. They're very stable. When you get above about 20, in order to have a stable nucleus, so this yellow band, especially the green portion, represents stable nuclei. That's the band of stability. Okay? And the ratio, the neutron to proton ratio of 1 is represented by this red line. So as you can see, as we get to higher and higher atomic numbers, we need to have proportionately more neutrons than we do protons. Okay? And that makes sense. As you get more and more protons, the repulsion between the positively charged protons gets more and more important, and you have to add more and more neutrons to kind of dilute that repelling force. And so the band of stability kind of veers up to the left and away from that 1 to 1 ratio. Now, one other thing I want to get out of this slide, or want you to get out of the slide, is atomic numbers greater than 83, and I think that is bismuth, but atomic numbers greater than 83, all of them are radioactive, okay? So if you look at a periodic table, and I wish I would have put one in here, if you look at a periodic table, you'll notice that beyond atomic number of 83, the atomic mass below the symbol will be a whole number. And it'll be in the atomic mass will be in parentheses. And that's because all of those elements bigger than 83 are radioactive, and because of that, we don't have a real good handle on exactly what their average atomic mass is. So we round it to the nearest whole number and put it in parentheses. Anytime you hear scientists say something about magic, it means they don't understand it. But the only thing I really want to point out at this slide is that in addition to that band of stability, where we know that as the nucleus gets larger, we need proportionally more and more neutrons to stabilize it, there is also an odd phenomenon that certain atomic numbers are just stable, period. And it turns out that if the atomic number, that is the number of protons, and the number of neutrons are both even, okay, there is more stability associated with that. So nuclide just means different types of elements or atoms. And there are a couple other rules like that which make the atom particularly stable or unstable. And scientists call those magic numbers. So I just wanted to let you know about that. You will need to know how to show the radioactive decay of elements that spontaneously decay. And as I said on the couple slides ago, if all atoms with an atomic number greater than 83 are radioactive, which means they spontaneously decay, okay? And we show that with, we call a decay series. And so if you have some element that's radioactive, let's say uranium-238 is a very common one, it will decay by whatever processes it needs to until it reaches a stable nuclei. And so one alpha decay may not be enough to make an element stable, so it may undergo 2, 3, 4, 5, 10, 12 decays before it stops, and we call these decay series. Let's look at the very common decay series for uranium-238. Uranium-238, and that's where a lot of the nuclear power we use comes from. We mine uranium. Undergoes an alpha decay first, okay? How do we know that? Because the substance we get when uranium-238 decomposes, how is it different? It has lost a mass of 4, okay? And thorium, it has gained atomic number of 2. What does that sound like? That sounds like an alpha particle, okay? So just so I don't have to go through this for every step, if it's a left pointing arrow, it's alpha decay. If it's a right pointing arrow, it's beta decay. So as you can see, uranium-238 decays into thorium, which then goes into prasinium, back to a different isotope of uranium, then thorium, then radon. So it's a multi-step process decay series. And this decay series actually happens on our Earth in nature. As I mentioned before, radioactive decay is always first order. And most scientists working with radioactive decay work in half-lives, talk about half-lives. And if you remember, the half-life for a first-order process does not depend on the concentration of the substance that you began with. The half-life of a first-order process is equal to 0.693 over K, the rate constant. So the half-life for any particular radioactive substance is a constant in itself, okay? It doesn't depend on the initial concentration, right? And so any type of radioactive process will usually have terminology talking about half-life instead of rate like we tend to in other chemical reactions. Of course, the shorter the half-life or the smaller the half-life, the faster something decays, okay? And also, the larger the half-life, the slower something decays, okay? And the smaller the rate constant is. So make sure you understand those relationships. Half-life varies tremendously from a fraction of a second to many, many, many years, okay? Depending on the stability of the nucleus and how it decays to become stable. You should also be able to interpret or determine the half-life from a graph of, we would normally think of concentration as on the y-axis if we're talking about radioactive decay, rather than talking in terms of molarity. Nuclear chemists usually actually talk about the number of atoms or the count. Same thing though, same principle. Time, of course, is still on the x-axis, okay? So how does the concentration of a radioactive process change over time? It has the same type of natural curve as for any first order kinetic process, okay? So it has a downward curve if you're just plotting concentration or quantity on the y-axis. Remember, we only get the linear relationship when we plot natural log of concentration on the y-axis. So anyway, if you're given a graph like this, and I ask you, what is the half-life? How would you go about determining that? Well, you look any place on the graph. Let's just start at the beginning and say, okay, we have 1,000,000 atoms right here. How long does it take to get half of that amount? Well, what's half of 1,000,000? It is 500,000. Okay, so here's 500,000. How long does it take to get from 1,000,000 to half that amount, which is 500,000? It takes 1 minute. So in this case, for this reaction, the half-life is 1 minute. And since it's a first order process, the half-life doesn't change, doesn't depend on concentration. So you should be able to get that same answer regardless of where you start. So let's start now at, let's just randomly pick here. That looks about 100,000. Okay, of 100,000 atoms at 3 minutes. And half of 100,000 is 50,000. So how long does it take to get from 100,000 to 50,000? As it approaches zero, it's obviously harder to see, but 50,000 is right there and somewhere around here. But anyway, it really should be 1 minute again. So the half-life should be 1 minute regardless of where you measure it. It should not change for a first-order process. Once again, nuclear chemists work with the kinetic rate laws or arrange them slightly different than what we're used to, so I want to point that out to you. You are used to seeing for a first order process something like this. Okay, and I've shown you how to rearrange that in case a problem talks about a percentage that has decayed or a ratio of what's left to what's gone. And I showed you that rearrangement to look something like this. Okay, and so now hopefully you can see the similarity between that rearranged form and the form that nuclear chemists use. And it's really identical, except they tend to talk about number of atoms, number of radioactive atoms, instead of concentration. But it's the same relationship. At this point, I want to divert a little and show you another equation that's really important when doing radioactive problems. This is an equation I will actually give you on the test, but you definitely need to know how to work with it. And basically it tells us that the amount of a substance at time t equals the amount of the substance originally times 1/2 or 0.5 raised to the power of capital T over little t. So let me tell you what this means. This is basically, okay, so big T is the total time that has passed. And T 1/2 is the half-life, whatever it happens to be. So I want you to think for a minute. That ratio in that equation, the exponent, T divided by T 1/2, what is that? Okay, total time divided by half-life. What is that telling us? Think for a minute. Total time that has passed divided by the time for one half-life. That is telling us the number of half-lives that have passed. The number of half-lives. So, for example, if you have a total time of 10,000 years and the half-life for a particular process was 2,000 years, how many half-lives have passed? That would mean 5 half-lives have passed. Okay? So this ratio in that case would be 5. So basically, every time one half-life passes, you cut the amount, the original amount you have, you divide it by 2, or multiply it by 1/2, same thing. And you do that as many times as for however many half-lives have passed. So let me work a problem with this for you, and then that's an equation you need to write down. There'll be practice worksheets with it too. So here's a typical problem. You have a radioisotope. I'm giving you the half-life. It's 238 years. If you start with 8 kilograms, how much of that will be left after 100 years? So anytime you have a nuclear chemistry timing problem, it's real handy to use the form that I just showed you, which is okay. So I'm going to plug in what I know so far. So we're trying to solve for AT, how much will be left. We know how much we started with, 8 kilograms. Okay, we're going to multiply that. I'm just going to change that to 0.5, make it easier to calculate. The total time that has passed is 100 years, and the time for one half-life is 238 years. So in other words, one half-life, one total half-life hasn't yet transpired. And so we started with 8 kilograms, so just using your common sense, it shouldn't be reduced even by half yet. So something more than 4 kilograms better be left. So let's go ahead and calculate that. So let's see, 100 divided by 238 is equal to 0.420. Okay, and so now I have to take 0.5 and raise it to that value. So now we have that the final amount is going to be 8 kilograms, and when I take 0.5 and raise it to the power of 0.420, I get 0.747. Make sure you know how to do this on your calculator. And that tells us then that the final amount of this radioactive substance after 100 years is 5.98 kilograms. So basically, this is always, you're always going to start with the original amount, and it's going to be multiplied by some fraction that's going to be less than 1, right? Because your original amount has to decrease. So this whole shebang, if you're entering it correctly, it'll be a fractional value less than 1. Alrighty. Radiocarbon dating using carbon-14 is a process that's used to figure out how long ago something that used to be alive died. So whether it's an ancient tree or a person or whatever, if it used to be alive, we can use radiocarbon dating to figure out how long ago that was. Now, carbon-14 is an isotope of carbon. The most predominant isotope of carbon is carbon-12, and there's also naturally a little bit of carbon-13 isotope. Carbon-14 occurs only in the upper atmosphere, not down here on Earth, but it gets incorporated into carbon dioxide, and so everything living, again, whether it's us or a plant, processes carbon dioxide through their body. And so we all have a certain ratio of carbon-14 in our body. Not very much, but a certain ratio of carbon-14 to the more predominant carbon-12. Carbon-14 has a half-life of 5,730 years. Now imagine that we're talking about a tree that undergoes actually takes in CO2 and then releases oxygen. And when it's alive, it's taking in CO2 that a certain amount of the carbon is carbon-14. When that tree dies, it's no longer part of the carbon cycle, so it stops processing new carbon-14, new CO2, and the carbon-14 that it had within it when it was alive continues to decay over time. So that original ratio of carbon-14 to carbon-12 when something is living starts to go down after that something dies. And depending on how much that ratio reduces, tells us how long that substance has been dead. So let me show you an example. This slide just kind of goes over what I just talked, but I know sometimes it's easier for you to read something and absorb it rather than to listen to me blab. So here it is if you need it. Here's a typical problem using carbon-14 data, and it is asking us to analyze a fossil, and according to the size of that fossil, it was expected to find about 240 grams of carbon-14 in it, and only 15 grams was found. And so from this data, it asks you to find out basically when this substance died, when this, let's say it was a tree, died. And so how they're wording this particular question is how many half-lives have passed. I'm going to show you a really easy way to do it, and then I'll do it using the equation. This easy way helps you just kind of understand what you're doing more. If we started with 240 grams of something that was radioactive, after one half-life, we would have 120 grams. After two half-lives, we would have 60 grams. After three half-lives, 30 grams. And after four half-lives, 15 grams. Look at that, right where we were supposed to be. How many half-lives have passed? 1, 2, 3, 4. 4 half-lives. So you're not always going to be this lucky with a problem and the math ends up being perfect, but at least it'll give you an idea of about how many half-lives. And so that's a really easy way to do it. So we have gone through 4 half-lives, and if the next question said how many years have passed, how old is this substance, when did it die is the right question. How long ago did it die? We've had 4 half-lives have passed. Each half-life is 5,730 years. So this substance, I should say, died 22,920 years ago. Now let me show you doing the same problem using the equation, and you can do it whichever way you prefer. But the equation I showed you a few slides ago, where the amount left over at some point equals the original amount times 0.5 raised to total time divided by the time of one half-life. So let's go ahead and solve for this. This problem told us the original and the final amount. The final amount was 15 grams, and the original amount was 240 grams. And assuming that we don't know, we're going to assume we don't know the 4 half-lives yet. We're going to assume we haven't worked, this is new, we haven't worked any of this problem. And so this problem is asking us how many half-lives. So they're basically asking us for this ratio. Remember, this ratio itself is the number of half-lives that have passed, the number of half-lives. So they're asking for the whole ratio. So we need to solve, we'll just call this x, this whole ratio. So we need to solve for x. All right, so let's do some rearranging. Let's divide both sides by 240, okay? And that is 0.0625 equals 0.5 raised to some exponent x, which will be our number of half-lives. How do you get rid of that x? As I've noticed that students over the last couple of years have struggled with logs, I think they've also struggled with this. So in order to get rid of an exponent, we are going to take the log of both sides. So I'm going to say the log of 0.0625 equals the log of 0.5 raised to the x. Okay. The log of 0.0625 is, let's see, minus 1.204. And the log of something with an exponent, the exponent comes down. So this rearranges to be x times log of 0.5. And then the log of 0.5 equals minus 0.3010. All right, so now what we have is this. So let's solve for x by dividing both sides by minus 0.3010. And so now we have and that then tells us, let's see, that x equals 4. Guess what? So remember, that is the number of half-lives. So I personally think using this equation is more complicated than doing it the way I did it originally. But again, the math isn't always going to be as beautiful as it was to just keep dividing it by 2 and get exactly what you want. So know both of these methods and practice some in the worksheet, and that should do the trick for you.